Okay. Well, welcome to the Post-Bayesian seminar. This is the second part of chapter 2. So the second seminar, we started off in June and we'll carry over into the summer. As usual, we thank all the organizers, including myself here. Just a little bit of kind of post-advertising. The workshop on Post-Bayesian methods was a big success. This was last week, held at UCL. I couldn't attend, unfortunately, but I know Jeremiah, Yan, and a couple of other people were there. And we had I think over 120 attendees, so really strong turnout. Thank you so much for attending, for those who were there. The talks were also recorded and will be uploaded soon. So in the same channel as the Post-Bayesian channel, I'm guessing. But just a few kind of housekeeping things. We have, again, the Post-Bayes website. You can subscribe to the mailing list. There's the calendar, and this is where you can find all the kind of other things like the YouTube link. The workshop's already done, but you can still take a look at the lineup on the website, which is quite nice. And a final bit of advertising. I'm not sure if you can still sign up for this anymore, but if you're in Singapore, you can come and say hi. We're going to have a satellite workshop at BaseConf focused on misspecification, but a lot of the people there will be kind of part of this Post-Bayesian community, so it'll be quite a fun little get-together. And for other people who are also going to BNP, some of us will also be there. So BNP 14 in Los Angeles. Okay, so as usual, we have kind of this standard format for questions and comments. You can use the Q&A function in Zoom. And the questions will be upvoted. We'll try to monitor the questions throughout. I think Yan usually monitors that. After the talk, then you can raise your hand in Zoom, and then you can just unmute and ask questions to the speaker. So this is the lineup for chapter 2. I gave the first introduction to the chapter. And today we have the great pleasure of having Professor Sandra Fortini give an introduction to the theoretical foundations on predictive Bayes. So Sandra is an associate professor in the Department of Statistics and Decision Science at Bocconi University. So all of you have probably heard of Bocconi University. It's sort of where all the best Bayesians are gathered. She's also a member of the Institute of Mathematical Statistics, as well as ISBA. And more of a personal note, I've been a huge fan of Sonia and Sandra's work since my PhD. Basically, all of their papers I've read, and I've loved like each and every one of them. She's made huge contributions together with Sonia to the field of predictive Bayes, both in terms of methodology and theory, and we're super lucky that we get to hear from her today. So I'm going to pass the floor over to Sandra now. Stop sharing my screen. Okay. So Sandra, you should be able to share your screen.
Yep. Okay. How can I remove this? Sorry. Okay. Okay. Can you hear me? Yes. Hope so. Okay. So thanks very much for this kind invitation, and thank you for organizing this series of seminar. This is a joint work with Sonia, and it's mostly based on a recent paper on exchangeability prediction and predictive modeling in Bayesian statistics. So the idea here is to try to explain a new way or a different way with respect to the usual one of introducing Bayesian modeling. So usually Bayesian models is given through priors, parameters and priors. And here we take a different approach, which is the one of directly modeling the distribution of the observations, and in particular using predictive distribution to model those observations. And the aim of this talk is twofold. From one side, I would like to provide conceptual motivation for modeling the learning through predictive rather than through priors. And on the other side, to highlight the advantages of this approach in terms of flexibility, interpretability, and computational simplicity. Now, to do this, we need to revisit the foundational principle of Bayesian statistics and what it means to be a Bayesian statistician. In this talk, I will consider a simple case of independent observation from a common unknown distribution, and the results generally can be extended to more general settings. So first of all, we want to understand what is a Bayesian model and how we can see Bayesian statistics as a learning process. So to do this, we want to contrast frequentist and Bayesian statistics. We consider observations in some space, in general, that's a Polish space, that are, let's say, independent from an unknown distribution F. Now, the frequentist approach estimates F through a database estimator, and it distinguishes between aleatory uncertainty, that is intrinsic randomness, for example, coin tossing outcomes, and epistemic uncertainty, so the lack of knowledge. So, for example, how the coin is weighted. In the frequentist approach, parameters are fixed but unknown, and the uncertainty about parameters is epistemic. The Bayesian approach is different. Usually, the Bayesian approach assigns a prior distribution to the unknown F, and then it updates the beliefs via Bayes' rule once the data are observed to get the posterior distribution of F given the data. So in the Bayesian approach, probability theory models all types of uncertainty, so both aleatory uncertainty and epistemic uncertainty. There is no distinction. And for that reason, parameters are treated as or are random variables. Now, the two approaches may look similar, but they differ conceptually. Let us go back to Bayesian statistics and see how we can interpret this as a learning process. So we have seen that Bayesian statistics models both observations and parameters within a single probabilistic model. And then learning is represented by conditioning, so by conditional distribution. So beliefs are updated via conditional distribution. In the simple setting that we are considering of independent observation from an unknown distribution, the unknown distribution F is treated as a random variable, and here to stress that it is a random variable, I will write F tilde, and F tilde as a prior distribution pi that express prior uncertainty or prior knowledge. And then conditionally on the value of F tilde, so if F tilde is equal F, the data are considered as independent, identically distributed from F. Now, this distribution together defines a joint distribution for both F tilde, the unknown random probability distribution, and the observation. So the Bayesian model is a probability measure on the product space of the space of probability measures on X and the space of the observations. And there is no formal distinction between parameters and observations in the sense that all unknowns are treated probabilistically. What is inference then? See, inference is just conditioning on the observed data. And there's a reason why there are no separate estimators in Bayesian statistics. So basically, once the model is specified, inference is an exercise in probability. So let's take up again our simple model where we have the observations that conditionally on the unknown random F tilde are IAD with distribution F tilde. So here F tilde infinity means the infinite product of F tilde with itself. And we have a prior distribution, so the distribution of F tilde. And we can see what are the properties of the empirical distribution. So the distribution of the observation. So delta here is a Dirac delta measure that puts a point mass on xi, and of the predicted distribution. So the distribution of next observation given past data. Now, it's quite easy to see that both the empirical distribution and the predictive distribution converge to F tilde, so the unknown random distribution. Now, from one side, as far as empirical is concerned, if we take a continuous, bounded continuous function G, and we integrate with respect to the empirical distribution, we have this average of the G of xi, and under the conditional probability P given F tilde, the xi are IID. So basically, this is a strong law of large numbers, and we have convergence to the conditional expectation, which is exactly the integral of G with respect to F tilde. And then if we marginalize with respect to F tilde, we have the convergence. Now, notice a key fact, and the key fact is that F tilde is a function of the sequence Xn, because it's the limit of the empirical distribution that depends on the sequence. Actually, we should say it's measurable with respect to the sequence and with respect to the tail of the sequence. Also, the predictive distribution converges to F tilde, and again, this is easy to see because the predictive distribution, En of A, is the probability that next observation is in A given x1, xn, and this is exactly the conditional expectation of F tilde of A. Now, this is a martingale, clearly by definition, and the martingale is bounded. It's actually a martingale measure, and it converges to the expectation of the same random variable F tilde of A given the whole sequence Xn. But then we have seen that F tilde is measurable, is a function of the axis, and therefore the conditional expectation is F tilde itself. So we have these two properties, F tilde, so the unknown random distribution, which is the distribution of the observations, is both the limit of the empirical distributions and of the predictive distribution. So now, if we consider again our model specified with the prior and the conditional distribution of the observations given F tilde, we have, as we have seen, a probability measure on the product space. And then by marginalizing over F tilde, we obtain the distribution of the observations alone. Now, since F tilde is a function of the sequence Xn, clearly the distribution of the Xn fully characterizes F tilde, and therefore also the joint distribution of F tilde and the axis. So basically, by these results, we can see then we can give directly a Bayesian model giving the distribution of the observations without the need of specifying the prior distribution, because then if the observation admits indeed the representation as conditionally IID given a random distribution, then the random distribution is completely specified. Now the question is, when does the distribution of Xn admit such a representation? And the answer is given by the famous Finetti theorem. So there exists F tilde such that the Xn are conditionally IID given F tilde if and only if the sequence Xn is exchangeable. And that means that the distribution of the sequence is invariant under finite permutations of the indices. So basically, that means that the order of the observation does not matter. So this theorem suggests an alternative way to define a Bayesian model. Instead of specifying the prior and the conditional distribution of the observation, the so-called model, the likelihood, we can specify directly an exchangeable distribution for the observation. And this is in contrast with frequentist modeling, because in Bayesian modeling, the probabilistic model on the observations accounts for both aleatory and epistemic uncertainty. And for example, even under random sampling, the observations are not independent because past observations give information about future observations. Now, what is the advantage of directly specifying an exchangeable distribution instead of the prior? Here we see a first point, which is that it eliminates the need to assign a prior distribution to parameters that in many cases lack a clear interpretation in terms of observables. Then we will see other advantages. But notice that a prior distribution is still implicitly defined, because we have seen that the distribution of xn implicitly defines a random distribution, and that random distribution, f tilde, is the almost sure limit of both the empirical and of the predictive distributions. Now, in practice, assigning the full law of a sequence in a way that it captures both intrinsic and the intrinsic aleatory and epistemic uncertainty is not easy. And predictive distribution can help in doing this. Now, it is well known that it's always possible to give the joint distribution of a sequence of random variables starting from the sequence of predictive distributions. And that result comes under the name of Ionescu-Tulcea theorem. In Ionescu-Tulcea theorem, we have a measurable space without any special properties, not even a polyspace, whatever space. Then we have a probability measure P naught on it. And then we have a sequence of kernels. So kernels means that we have functions that are both functions of subset of x and of x1, xn, with the property that with respect to x1, xn, the function is measurable. And for every fixed x1, xn, Pn as a function of A is a probability measure. Under these very weak assumptions, there exists a space and the stochastic process on that space that has P naught as the distribution of x1 and the kernels as the predictive distributions. And moreover, the joint distribution of the observation is uniquely determined by the sequence of the kernels. Now, using predictive distribution gives an advantage, because predictive distribution naturally reflect epistemic uncertainty. So Pn, which is the distribution of xn plus 1 given x1, xn, encodes our beliefs about xn plus 1 given the data. Now, in this perspective, a predictive distribution is not representing a physical mechanism generating xn plus 1, but it's representing a learning rule. So what we learn about xn plus 1 when we observe x1, xn. And we refer to this predictive perspective as predictive modeling. So in predictive modeling, reasoning focuses on observable quantities, the x's, and on how the sample informs prediction. And predictive modeling is intriguing as a form of Bayesian learning without a prior, because no explicit prior is required, although a prior may be implied by the predictive structure. Here is a very simple example with binary random variables taking values 0, 1, where the learning is done through reinforcement. So if we look at the predictive distribution, so the probability that next observation is a 1, given past observation, this is a linear function of the number of ones in the sample. And that means that each time we observe a 1 in the sample, we increase the probability of observing further 1 in the future. And vice versa, if we observe zeros, then we decrease the probability of observing 1 in future. So learning occurs through recursive predictive updates. And each observation incrementally adjusts the belief about future outcomes. Now we want to say a bit more about exchangeability and prediction. We have seen that the UNESCO-Tulcea theorem allows to build the distribution of a sequence starting from the predicted distribution. And UNESCO-Tulcea theorem imposes no constraints on those predicted distributions. You are completely free to give them as you like. But the question is, what constraints must the predicted distribution satisfy in order for the sequence to be exchangeable? And it can be proved that there are two very simple properties that ensure the exchangeability. So Xn is exchangeable if and only if the two properties here hold. The first property tells you that the predicted distribution are symmetric with respect to past observation, are symmetric functions of past observations. And the second property tells you that the predictive distribution for next two observations is symmetric. So the predictive is symmetric in next two observations. So for example, if we go back to our binary random variable example, we can see that the first condition holds because the predictive distribution is a function of the sum of the xi, which is clearly a symmetric function. And then to check the second condition, we only need to show that the probability that next observation is 1 and then the next one is 0 is the same as the probability that next observation is 0 and then we have a 1. And here just a little bit of algebra show that this is indeed true. So the sequence is exchangeable. Actually, the prior distribution here is known and it's the beta distribution. And the unknown probability of 1, f tilde of 1, is both the limit of the frequency of ones and also of the probability that next observation is 1. Now, notice that we have two conditions. The first one is that the predictive distribution is symmetric in x1, xn, and the second condition is that the predictive distribution of next two observations is symmetric in those observations. And the symmetry with respect to past data is not sufficient for exchangeability, and it's easy to build an example. Here is again an example where the random variable takes values 0 and 1. The first two observations are equal to 1 with a fixed probability alpha, strictly between 0 and 1. And after that, the other observations are equal to 1 with probability which is equal to the frequency of 1 in the sample. And clearly, it's not possible to have 0, 0, and then 1, because x3 is 1 with a property which is equal to the frequency of 1, which is 0. But on the other side, we might have 0, and then 1, and then again 0. And therefore, the joint distribution is not symmetric. So actually, we need both conditions to get exchangeability. But it's, I think, quite clear that assigning, so defining maybe new predictive distribution that satisfy those conditions is not an easy task in general. Now, a way of simplifying the assignment of predictive distribution is to use predictive sufficient statistics. We have seen by the characterization theorem that the predictive distribution is symmetric with respect to past observations. And we can revisit this property by saying that the predictive distribution is a function of the empirical distribution, because the empirical distribution takes into account the values of the observations, but not their order. Now, if the predictive distribution depends on the empirical distribution only through a function of it, so a statistic, so if there exists Qn such that the predictive distribution is a function Qn of T of the empirical distribution, then we say that Tn is predictive sufficient. And that means that to make a prediction on xn plus 1, we actually don't need to know the values x1, xn. We just need to know the value of this statistic, T of them. Now, if the sufficient statistic takes values in a finite dimensional space, we can expect that the model F tilde is a parametric one. And this is indeed the case under regularity condition. So if we already know that the empirical distribution converges to F tilde, if T is continuous, T of the empirical distribution will converge to T of F tilde, and then under regularity condition of Qn, there exists a function Q such that Qn of T of F hat n converges to Q of T of F tilde. But on the other side, Pn converges to F tilde, and that means that F tilde is equal to this function Q of T of F tilde. And T of F tilde takes values in a finite dimensional space, so it's a parameter. So in this case, the model is parametric, and the parameter is the limit of the sufficient statistic. Now, the regularity condition ensures that small changes in the sufficient statistic do not produce abrupt changes in the predicted distribution, so a sort of continuity. Under further assumption, the parametric model is also dominated, and the assumption is that the predicted distribution are all absolutely continuous with respect to a dominating measure lambda, and that the convergence, now in this theorem, the convergence is a weak convergence, so with respect to weak topology, if we instead also ask convergence in total variation, then we get a model which is dominated. Now, here I show very simple examples of predictive construction through reinforcement learning. The first one is the very well-known Polya sequence example, which is similar to the previous example with binary random variables. Here, X is a Polish space, so matrix separable and complete. And the predictive rule is a function of a measure here that gives a point mass to each observations xi. So basically, the numerator here is a measure, and then we renormalize the measure to get the probability measure. And it can be proved that this construction corresponds to a Bayesian model where F tilde has a Dirichlet process distribution. There is also an Earn interpretation of this predictive construction where the observations are represented by colors. So we start with an Earn that contains alpha black balls, or alpha is the parameter here. And then at each step, if we observe a color ball, then we return it and add another ball of the same color, so we reinforce the color. And each time we observe a black ball, then we draw a new color from the distribution P naught, and then we add a ball of that color to the Earn together with the black ball. So again, we have the idea of reinforcement learning, because when we observe a color, we reinforce the probability of getting the same color in the future. An extension of this predictive construction is the kernel-based Dirichlet sequence, where the structure of the predictive distribution is similar, but the point masses, delta xi, here are replaced by a smoothed version via a probability kernel K. So basically, instead of putting a point mass, we spread the mass with a smooth probability measure. Now, it can be proved that exchangeability of this model holds if and only if the kernel have a very specific expression. So if and only if the kernel is P0 conditional on sigma algebra on X. for some sigma algebra G. And in particular, if the kernel is absolutely continuous with respect to P0 for all x, the associated Finetti measure, so F tilde, is a mixture model where the component distribution have known disjoint support. So basically, we can think simply to this situation as random histograms where we reinforce an interval containing the observation that just arrived. Now, this example and the fact that only in very specific case we have exchangeability highlights that exchangeability can be a strong constraint, especially when we want tractable prediction rules and model flexibility. So we may think about going beyond exchangeability. Actually, there are several reasons to relax the exchangeability assumption, even when modeling homogeneous observation. To derive predictive distributions with a simpler or closed form expression, to increase model flexibility, to reduce computational costs, having closed form updating, and so avoiding MCMC-based methods, or to bypass the need for explicitly specifying a prior and using parameters. Now, the key question is, how can we relax exchangeability while preserving the idea that observations arise in a way independently from the same unknown distribution? And to answer this question, it is usually to look a bit closely to the exchangeability assumption and to its structural components. Now, it's easy to see that an exchangeable sequence is strongly stationary. So the distribution doesn't change if we apply a lag of time. And moreover, an exchangeable sequence satisfies a condition which is called conditionally identically distributed. And that means that given past observations, all future observations are marginally identically distributed. So I have some observation, and then I have to make a prediction on future observation, and I give the same marginal distribution to all future observation. If a sequence has this property, we say that the random variables are conditionally identically distributed. Now, strong stationarity and CID condition characterize exchangeability. There is this very nice result by Kallenberg showing that exchangeability is equivalent to stationarity plus CID. So a sequence is exchangeable if and only if it is both stationary and conditionally identically distributed. Now, this is a bit surprising because if we look at the definition of strong stationarity and CID, there is no way of reverting the time, okay? And indeed, the proof is not trivial, and it's based on the ergodic theorem. So we can think about relaxing the assumption of exchangeability by only requiring the CID condition, thereby giving up strong stationarity. So under the CID condition, all future observations share the same conditional distribution given the past. And of course, this is again a property that would be difficult to check, but we can simplify very much this assumption because it's actually sufficient that next two observations are conditionally identically distributed to get the CID condition. And you can understand why this is true. From one side, we can iterate the procedure, and from the other side, we can marginalize, and so we marginalize over past observations. And what is nice is that this condition, sufficient condition for CID, is equivalent to a martingale condition on the predictive distribution. So a sequence is CID if and only if the sequence of predictive distribution is a martingale measure. And again, this can be seen immediately from the previous condition here, because when we compute the conditional expectation of the predictive distribution of xn plus 2 given x1, xn, using just the properties of conditioning, we see that this is exactly the probability that, so the distribution of xn plus 2 given x1, xn. And therefore, we can say that a sequence is conditionally identically distributed if and only if the sequence of predictive distribution is a martingale measure. And we know that martingales have very nice property that we can exploit. Now, how close is CID to exchangeability? It's quite close, actually. First, the observations are marginally identically distributed. The sequence of the predictive distributions is a martingale measure, and it's a bounded martingale because it's a probability measure. And therefore, it converges to a random probability measure, let's say F tilde. Then, using martingale methods, it's not difficult to see that if the sequence of predictive distribution converges to F tilde, to a random probability measure F tilde, then also the empirical distribution converges to the same F tilde. So for a CID sequence, also the empirical distributions converge to F tilde, which means that in a way, F tilde represents exactly what we want to learn. If we could observe all the x's up to infinity, we would have the distribution of the empirical distribution for every n, and we would know everything about the observation. So F tilde is indeed what we're looking for. And furthermore, now we know that the sequence of predictive distribution converges to F tilde, and there is a nice property proved, for example, on the book of Aldous, showing that if the sequence of predictive distribution converges to a random probability measure, F tilde, then the sequence Xn is asymptotically exchangeable. And that means that there exists an exchangeable sequence, let's say Zn, such that the tail of the sequence Xn converges in distribution to Zn as n goes to infinity. And the directing random measure of the sequence Zn is exactly F tilde, which is the limit of both the predictive distribution and the empirical distribution. Thus, a CID sequence implicitly defines a prior distribution, which is the law of F tilde. Here is a simple example that extends the Polya sequence that we have seen before. So the structure of the predictive distribution is similar, but we have those weights. The weights here are positive random variables. And under the assumption that the weight of xn plus 1 given x1, xn, so wn plus 1, is conditionally independent. So the weight is independent of the value of the observation. The sequence xn satisfies the CID condition. And for example, a scheme like this could be used when we have different levels of reliability across observations. So we want to weight observation differently. Now, if we have a CID sequence, we have a problem. The problem is that we know that there exists an F tilde that drives the distribution of the axis, but the prior and posterior distribution, so the conditional distribution of F tilde given the data, is generally unknown in closed form. However, we can simulate from the posterior distribution by exploiting the convergence of the predicted distribution to F tilde. Here I consider the simple case where the observations are real valued, and therefore I suppose we want to simulate from the posterior distribution of the distribution function of F tilde that I call F tilde of t. So let's see how to generate a sample from the posterior distribution f tilde of t given observation. First of all, we can select a grid of points on the real line, and these are the points where our f tilde is evaluated. Then we can sequentially generate future observations starting from n+1, because we already have x1, xn, which is our sample. And we can generate our observations from the predictive distribution. Then, using the extended sample, so the first part is the true sample, and then we have the generated sample, we can compute the predictive distribution function at the points t1, tk. And if capital N is large, since we know that the predictive distribution converges to f tilde, this vector approximates a sample from the posterior distribution of f tilde in t1, tk. So we have one sample, and then we can repeat the same procedure n times and get a Monte Carlo sample of size n from the posterior distribution of f tilde in t1, tk. Now, if n is large, we can also get an asymptotic approximation of the posterior distribution. So let's start from the last part of this theorem. So we are giving an approximation of the posterior distribution of f tilde of t. So we are still think of real valued random variables. So this is a random distribution function given x1, xn. And we can approximate this posterior distribution with a normal distribution with mean Pn. Pn is exactly the condition expectation of f tilde of t given x1, xn, and a certain variance, Vnt divided by Bn, with Bn that goes to infinity. Now, what is Vnt and what is Bn? Now, first of all, we need to look at the conditional expectation of the square predictive updates. Here, Pn of t minus Pn minus 1 of t is the update of the predictive distribution that we do when we observe xn. So we consider the expectation given past data of the square predictive update. And then alpha n is a sequence of numbers that basically represents alpha n squared, basically represent the size of this condition expectation. So we have a sequence, and we assume that there is convergence of the renormalized condition expectation of the square predictive updates to a strictly positive random variable u. At that point, we have the sequence alpha n, and alpha n goes to 0 because the predictive update go to 0 because Pn converges. And then we can take Bn, which is 1 divided by the remainder of the series alpha k squared, which is a converging series. Okay, so that gives Bn, which is here in the denominator. And then what is Vnt? Vnt is a statistic, which is based again on the predictive updates. Notice that we stop at n, so we can compute it once we have the predictive distributions, renormalized by the sequence alpha n squared. Now, this is given for just one t, but basically the same result extends to the case where we want an approximation of the conditional distribution of f tilde in different points t1, tk. And of course, in that case, we have a multivariate normal distribution. This result allows for the construction of asymptotic credible intervals for f tilde of t that are centered in the predicted distribution, and then the size of the interval depends on Bn, And we have seen that Bn depends on the alpha k, so on how fast the predictive updates go to 0, and then on V and T, that again depends on the predictive update. Now, typically, when we look at the size of a predictive update, typically, and this is the case, for example, generally for exchangeable sequences, the size of the absolute value of the predictive update is the same as the size of the update of the empirical distribution. And in the case of the empirical distribution, that can be easily computed, is asymptotic to 1 over n. So in most cases, actually, Bn is exactly n. So we have square root of Vnt divided by square root of Bn. Now, notice that this approximation is not a consistency result in the classical sense. So in the classical posterior consistency result, like Best and von Mises theorems, the asymptotic is given under the assumption that the observations are IAD from a true distribution F naught. In our setting, we don't have true distribution, and the asymptotic result is given under this distribution of the observation Xn, which is defined by the sequence of predictive distribution. So the point is that the aim here is different. It's not a consistency result, but it's a way of providing an asymptotic approximation of an unknown posterior distribution. Of course, consistency and contraction rates are interesting problems, as far as I know, quite open problems. Now, how can we in practice give learning rules that give nice properties for the sequence Xn and also that are easy to compute and can be computed in closed form? We can think about a general scheme where we assume that the predictive distribution is a function Qn of a predictive sufficient statistic Tn, such that Tn can be easily updated as a function, known function, of the previous value of the sufficient statistics and the last observation Xn, the current observation Xn. If we have a predictive rule of this kind, then we have a learning rule which is very easy to compute and very fast, and we only need to store the sufficient statistics, so not all the data. And if we use appropriate choices of the functions Qn and Hn that are known functions, then we can get desirable properties of the sequence Xn, such as, for example, asymptotic exchangeability. Now, notice that many common Bayesian models admit this representation. So here, just a very simple example. The previous example of the binary random variables, which is, so where the probability the next observation is 1 is written in this way. Now we can rewrite this model sequentially using as the predictive sufficient Tn. Here is the sample frequency of ones. And here the sample frequency of 1 can be easily computed from the past value and Xn. And analogous for the Polya sequence. So the same in this case, Tn is the empirical distribution. Another example in the literature that can be rephrased in this way is the measure value Polya sequence, where the predicted distribution is a normalized measure. So we can see the early interpretation. So we have X, which is the space where the random variables take value. And each subset starts with a mass, T naught of B. And then at each step n, B receives an additional mass, R xn of B, that depends on the observation xn. In general, measure value Polya sequence is not exchangeable, and it can be proved that it is exchangeable if and only if it is what we have seen before, so a kernel-based Dirichlet sequence. So in this case, we need to have the reinforcement must be such that the reinforcement of the whole space does not depend on the observation. Then we can play with a constant in such a way that the reinforcement is a probability kernel, and it's exchangeable if and only if the probability kernel is P0, which is the starting distribution, conditional on a sigma algebra G. Now I'm going to show two, in a way, new examples of construction, predictive constructions. The first one is a learning rule for mixtures. So we have observations taking value in a space X and a measure lambda on X. And the distribution of the observations is a mixture model, which is absolutely continuous with respect to lambda. So K is a kernel, a density kernel, and the mixing distribution is unknown. So at each time n, we have the predicted distribution for next observation is given by the mixture model with Gn, and the learning is about Gn. Here, the learning is done using Newton's algorithm that was designed to approximate the Dirichlet process mixture model. So here, Gn is updated. So Gn is our sufficient statistics, and it is updated as a new observation xn becomes available by taking a convex combination of the previous Gn-1 mixing distribution. And, okay, this product is the posterior when the prior is Gn-1, and we have just one observation, which is xn. So here we take Newton's algorithm, but instead of interpreting it as an algorithm, we interpret it as a learning rule. And with this learning process, we have nice properties. So first, Gn is a martingale measure, so it converges to a random probability mixing measure G tilde. Xn is CID, conditionally identically distributed, and therefore it is asymptotically exchangeable. And this asymptotic directing random measure is again a mixture measure where the mixing is G tilde is the limit of Gn. Tn in this way defines implicitly a novel prior which is absolutely continuous with respect to lambda. And although the posterior distribution remains unknown, it is possible, basically, as we have seen before, to sample from it using the predicted distribution and to give asymptotic Gaussian approximation. The second learning model is based on loss function. Here it is applied to binary classification. So at each time, step n, a pair xn, yn is observed. Xn denotes a feature vector, and yn is a binary label. We define the model through the predictive distribution, where we have the marginal distribution of x, which is either known or estimated separately. And then the conditional distribution of y given x is a generalized linear model with a known function g. For example, it could be the logistic function. The function depends on a known parameter beta, and the learning is about beta. How do we learn about beta? We learn about beta by using the so-called online gradient descent. And that means that at each new observation xn, yn, we update beta, going from beta n-1 to beta n by moving in the direction that minimizes the loss function. with a learning rate alpha n that goes to 0. And under my assumption, beta n, the parameters converges to a random limit. Furthermore, the sequence beta n is a martingale, and that means that the current estimate beta n is the posterior mean of beta tilde. The sequence xn yn is asymptotically exchangeable, and the directing random measure of the sequence is such that the conditional distribution of y given x is a Bernoulli distribution with parameter g of x beta tilde. Now, without going to details, we can, as we have seen before, both sample from the posterior distribution of beta tilde given the data, and also give an asymptotic approximation, Gaussian asymptotic approximation. And in this procedure, notice that the knowledge of the distribution of the feature Px is actually not required, although it enters the model. So just to close, we have seen that the Bayesian paradigm provides a powerful framework for learning from data and performs well in many contexts. Here, I mean prior posterior usually way of giving a Bayesian paradigm. But an alternative perspective is to directly model the learning process rather than starting from a prior. And this approach offers greater flexibility and often leads to more interpretable models, and specifying simple predictive distribution can simplify computation without sacrificing key properties such as asymptotic exchangeability. Of course, there are many open questions. Just to mention some of them, the study of consistency and contraction rates. And here we have seen a very simple case of exchangeable sequences and the extension to more general symmetries and complex models. Thank you.
Thank you so much for the wonderful presentation. Let's give Sandra an online round of applause. Maybe we can open the ground for any questions from the audience. So feel free to just unmute if you have any questions. I'll start with the first because obviously I have like a million questions, but I'll try to keep it like short. My first question is about this CID condition you mentioned. So it looks like it's sort of as weak as you can get from exchangeable, like it's sort of the best you can do. But do you think we can make it even weaker and still have something that feels kind of exchangeable or still works under IID sampling? Like, can we go all the way to just as weak conditions as possible and one day use some really crazy predictives, for example?
Absolutely, yes. So for example, in the last example with binary classification, the CID condition does not hold. And of course, we need some convergence. And the easiest way of getting convergence is using martingales, but that's not the only way. So here there is a martingale, and the martingale is on the sequence beta n. But even the martingale condition is not needed as far as we get convergence to something which is random. We need something which is random to get something which is similar to a Bayesian model, where the distribution is random because we don't know about it, and then we compute the conditional distribution given the data. So for example, one direction that could be interesting to see is whether stochastic approximation can be used instead of martingales, or quasi-martingales, for example, that have basically the same properties of martingales. So I think there is a lot of space to explore different directions and get different models. Absolutely, yes.
Amazing, thank you. Yeah, that gives me hope. Any other questions from the audience? Maybe I'll end with one more question, so I won't take up everyone's time too
Yeah.
much, and I'll save my questions for when we meet in person. You mentioned the extension to structured data, and I was curious, like, because I've been stuck on a similar problem where this notion of tail measurability that you mentioned was really interesting because it feels like when you say f is tail measurable, it's almost like an IID sequence, right? It's kind of like a
Mhm.
strong law.
Yeah.
Have you ever seen any other objects be like tail measurable, like maybe in non-exchangeable settings? Like I've been struggling a lot with thinking of kind of what the tail measurable object is when you're not exchangeable or not IID, kind of.
Okay, that's a very good question. This is also connected to, for example, the invariance when we have some, for example, stationary sequence, and you can play also with the invariant sigma algebra that probably is connected, but actually I don't have an answer. So I don't know. I don't know, except for the case of exchangeability. I don't know about other situations. That's a very interesting question, but
Well,
I
we can
don't.
talk more about it
Yeah,
in
yeah. It's a
P14.
very,
So
very, very interesting point. Yes.
okay, well, thank you so much for your time, Sandra. If there are no other questions, then we're gonna call it a day. That was an amazing talk. So I'll
Thank you to everybody to be here and to listen to my talk.